Professor, he has received doctoral degree from IIT Madras. He completed postdoctoral research from Kyushu University, Japan. He has developed mechatronics and instrumentation laboratory at IIT Indore. His research area of expertise, which includes laser-assisted surface processing, micromachining, smart materials, and shape memory alloys. He has published more than 100 research articles in various international journals. He has filed 6 patents. He has executed many of sponsored projects from different funding agencies, such as DST, SER, JSPS, DRDO, MHRD, worth of more than 10 crores. He has closely worked with industries such as Volvo, HR, John Deere, Wabco Technologies, and other etc. Currently, Professor, he is the Dean Research and Development at IIT Indore. On behalf of IIIT Tiruchirappalli and the participants of this faculty development program, I welcome Dr. I.A. Balani to deliver his session on characterization of shape memory alloy. Welcome, sir.
Thank you very much for this opportunity. So I am glad to be a part of this particular forum. So now I'm just sharing my screen. Okay, so basically the talk which I am going to discuss today is related to manufacturing and characterization of shape memory alloys for different functional applications. So what I would like to suggest is, so as far as these topics are concerned, so these topics are executed in our laboratory with respect to different problems which we have faced with respect to shape memory alloys and how we have addressed those problems. So that those things I will be discussing today in this talk. So as far as this shape memory alloy is concerned, so shape memory alloy are a class of smart materials. So when we talk about the smart materials, so these are some kind of peculiar materials, so which behave slightly different from the other materials. Okay, so one good example with this shape memory alloy is like this is responsive to heat. So I'll be showing you a video. How does it work? So hope you could be able to see that video. So here, if you see, so there is a kind of lotus flower kind of arrangement is over here. So this lotus flower is completely made out of shape memory alloy metals. So there is a amount of heat is applied to this shape memory alloy metallic layer using a hot air, and then when we are trying to cut off the heat, it comes back to its shape. Okay, so this is a kind of a peculiar characteristics of this shape memory alloy. In fact, this is from one of our collaborators' laboratory where they have demonstrated such kind of lotus petal kind of arrangement. So this will give you an overview about how a smart material is different from the conventional materials. So there are wide varieties of smart materials which are available. So basically, this slide will give you a clarity about the different varieties of smart materials which are available, which includes shape memory alloys, which is responsive to heat, a piezoelectric material, which is responsive to electrical part, EM, basically with respect to load and with respect to EM of characteristics. Then there are some certain amount of ionic polymers which are available, and then there are certain amount of magnetic shape memory alloys which are available, where a magnetic field is employed, and based on the magnetic field, so you can just actuate this. Okay, so as far as these smart materials are concerned, so when we try to look into these class of these smart materials, so obviously you may ask me a question. So what is the key parameter in selecting the smart materials? So based on my application, so I try to discretize my application based on my actuation stress and then with respect to actuation stress, as well as my actuation medium. So these are some of the key aspects which basically helps me to identify the type of smart materials which I need to select. Okay, so based on that, you can select the smart material. So in this lecture today, we will discuss only on shape memory alloy related aspects. Okay, so as far as this shape memory alloy is concerned, so this shape memory alloy was first invented in the year 1938. Basically, So it is the commercially available shape memory alloy. We call it as nitinol, which is nothing but a nickel titanium naval ordnance slab. So it's a copyrighted material from there, which has been used for some of the defense related applications. In fact, once we went to Russia, we could found that they have been using this material much more time than US has been using it. So what they have done is they have used those materials in the form of a heat engine, and then it was used for loading the bullets in a firing artillery. So such kind of arrangements they have made. So now, if I closely observe, what is the mechanism behind this shape memory? So this, as far as when we try to look into the mechanism of it, it is similar to the phase transformation characteristics which is happening in any material. So let us consider. So I have a piece of ice. So I am just heating this ice, it becomes a liquid. Further heating this liquid, it comes to a gaseous phase. So now, so here the material is going to be almost the same, but there is going to be a phase transformation which exists, which makes it to change its functional property. In a similar fashion, in the case of shape memory alloy also, so we have an austenite phase, we have a martensite phase. So this shape memory alloy characteristics is basically switching between an austenite phase and a martensite phase. So to give you a better clarity, so here there is a video where you could see there is a weight which is tied to a spring, SMA spring. So this video we have taken in our laboratory. So what we are trying to do is, so because of the weight, it tries to pull the spring. And when I try to apply an electrical biasing to it, it tries to come back to its shape. Okay. So initially the spring is in the martensite phase. Now I am deforming it using a weight. So this we call it as the deforming the martensite. Now it is deformed. This is the deformed martensite. Now when I try to apply an electrical biasing to it, it forms an austenite phase, and then it again comes back to the martensite phase. Okay. So just to give some more insight about this. So this is one video. I think it's not playing. So I can just show this video later, where we have used a hot water actuation to actuate it, so that we can see how does it move. This is hot water actuation, where there is a vessel is kept and there is a hot water which is placed over it. We are trying to deform the spring and we are trying to insert it inside the hot water. It comes back to its original shape. You could see how good is its responses, that when the student tries to put it out, immediately it takes a shape. So this is the deformed spring. So but we are just inserting the spring inside a hot water, and it tries to curl its shape. Okay. So it shows you a capability of the shape memory alloy, so which is switched between the austenite and the martensite phase. Okay. Now, so now it is working. So this is on the martensite phase. It is getting deformed to an austenite phase. Okay. Now you may ask me a question, that in the case of a spring, so how they are training it in such a way that the required shape is such. So for this, we need to train the shape memory alloy based on our requirement. So basically, since we know the fundamental that the material has to be taken into the austenite phase, it is the switching between the austenite phase and the martensite phase. So the material is taken to the austenite phase. It is, we can just apply a constraint to it. So this is one such constraint. For example, if I need to, when I try to place it in a hot water, I need to get a deformation, something like this. And when I try to quench it in a cold water, it has to be returned to its shape. So originally it will be in this shape, and when I try to put it in hot water, it gets transformed to this shape. So in order to get this shape, so what we can do is we have a small steel jig. So over the steel jig, we can just put these materials and we can just train these materials. Training is nothing but we are going to heat these materials in this particular furnace, and then we can go for a continuous heating and cooling. That is, we go for a heating and then we immediately quench it in a liquid nitrogen environment. So when we try to do this back and forth, then we can achieve the required structures coming out of it. Okay, so as far as this shape memory alloy structures are concerned, so there are wide varieties, or I would say there are different materials which exhibits this shape memory alloy. Commercially, if we try to look into it, nickel titanium is one of the commercial material which has a capability which exhibits shape memory alloy behavior. Okay, so so in that we have NITI, CU, etc. So even people have attempted in going for different types of quaternary alloys, ternary alloys, etc. So that you get different combinations of nickel titanium shape memory alloys. Now, in the case of copper-based shape memory alloys, so we can there are wide varieties of copper-based shape memory alloys which are available, so which has both ternary and quaternary structures. But fundamentally, when do we need to go for nickel titanium and when do we need to go for a copper-based shape memory alloys? So in the case of nickel titanium, if my actuation range is, if my actuation temperature is within the range of 80 to 130 degrees Celsius for nickel titanium based shape memory alloys, and if my actuation is in the range of 250 to 350 degrees Celsius, then I go for a copper based shape memory alloys. So apart from that, there are other shape memory alloys which are available, like Fe based shape memory alloys, etc. So those have a potential application towards low temperature sensing, as well as it has a potential application towards high temperature sensing, as well as towards robotic applications also. Okay, now this is a kind of training which we have done in our laboratory, where we want to make an ohm kind of structure, something like this. So when we try to heat it, we would like to get a straight plate, and when you try to cut off the heat, we want to get an ohm kind of structure. I think someone has unmuted. Okay, so this is a kind of a tedious process which happens, so that this will be helpful for us to train the required structure. Okay, so this is one of the key aspects in training a shape memory alloy. But the major problem in this is this requires a huge amount of energy even to train the shape memory alloy to a particular structure or shape. So with this as an idea, so let me just give you an overview about the different challenges involved in shape memory alloys, how we have addressed these challenges, and how we have characterized these shape memory alloy for in overcoming these challenges. Okay, so the first problem with respect to shape memory alloy is a tedious training process, because even if you want to get a displacement of something around 1 mm or even 2 mm, so I may need to go for a continuous training. That is, I may need to heat it, then I may need to quench it, which is very difficult. Okay, so this is one thing. Second thing is like influence of composition. See, commercially, when we try to buy a shape memory alloy, so we get a shape memory alloy, either we get a nickel titanium material, or we get a copper based shape memory alloy. We don't get a copper based shape memory alloy, but we get a nickel titanium which is commercially available. Okay, so it is very difficult to investigate what is the influence of different composition. Like we may feel that there might be, and when we try to include an intermetallics, its property may improve, or sometimes in some cases we may need to employ these kind of structure for some kind of functional applications. Because of the limitation in usage of the material, it will be difficult for us to proceed further. Okay, so such kind of different attempts are available. Third important aspect is in the video, if you could see, so you may ask me a question that how many life cycles does this shape memory alloy can withstand? Because see, one set of actuation is happening because of the weight. That is one kind of displacement is happening because of the weight. And now you are trying to supply a heat in the form of an electrical pulse, and we are trying to get back to its original shape. Okay, so it is something like there is a thermomechanical behavior which exists in this material. So when we are trying to use it for some kind of functional application. So whenever there is a thermomechanical is there, so we all know obviously there is a chance of oxide formation. So when there is a chance of oxide formation is there, slowly it will start introducing a defect into the structure, and this defect will try to stop my structural, structural formation, or it will try to hamper my functional behavior. So this is one of the important aspects with respect to the thermal mechanical behavior. So we need to study this thermomechanical behavior in detail. So this is one of the important aspects. And the fourth important challenge is commercially, when you try to get some kind of shape memory alloy structures. So we get the shape memory alloy in the form of a wire form, or we get it in the form of a sheet, or we get it in the form of a plane. But for example, if we want to get it in the form of a spline, or in the form of some kind of star kind of structure or something, it is very difficult to, in fact, it is not possible to get it in the commercial market. So these are some of the challenges which basically kindles us to look into these challenges and address these challenges. So in that aspect, the first challenge what we took is towards overcoming this tedious strain. Okay, so so before going into this first challenge, if there is any questions or queries, I would be happy to address it, and then we can go to the first challenge. If you have any doubts in the fundamentals of shape memory alloy, we can have a discussion on it. Okay, so if not so let us start with the first case study, where we are trying to manufacture a concept called shape memory alloy Bimorph. The main application of the shape memory, objective of manufacturing the shape memory alloy Biomorph is that I need to reduce the tedious straining. So that is one thing. Second important thing is I would like to use this for some kind of micro robotic applications. Okay, like these are some kind of dragonflies which are available. So in the case of dragonflies, we see a small delicate wing kind of structure which is available. So this wing kind of structure will vibrate at a very high frequency. So when it vibrates at a very high frequency, it tries to create a lift force, and finally it will help to lift up. Okay, so people have attempted such kind of system. So in our laboratory, so what we did is, so we went for a concept called Bimorph. So the concept of this Bimorph is, I have two layers. So one layer is like this, and the other layer is like this. So this is a kind of a shape memory alloy which is available, and this is the polyamide structure. Okay, so this we have used a small Kapton polyamide. So what happens is, like one way of actuation we would like to achieve using a shape memory alloy, and the return stroke happens because of the polyamide. Okay, so it's a kind of a functionality where you don't need to go for a training. So when you are fabricating your structure itself, so at the time itself you can go for a deposition, so that this deposition, so when you are going for a deposition, you are just programming the material, so that you are programming the material in such a way that whatever displacement you require, so accordingly you are trying to program the material. Okay, so here in this case, what we are doing is, so we have a polyamide. So this is in the before deposition, and this polyamide is strained in a fixture. So in this fixture, what we are doing is we are trying to apply a strain to this fixture, so that we want to get a complete actuation coming out of it. Okay, so this is being strained, and then we are going for a thermal evaporation in such a way that we are trying to hang it, and then we are trying to have a boat kind of arrangement which is available. So in this boat, we are planning to have a material. So in fact, I will be having a experimental schematic of it. So this is an thermal evaporation system where we have kept the shape memory alloy, and we are just heating the shape memory alloy. In the meantime, this is a polyamide structure which is available. So in this polyamide structure, we are trying to apply a constraint, and then there is a continuous deposition of the material which takes place. So internally, if I try to look into the fundamentals behind it, like I am trying to apply a strain to it. When I am applying a strain, I am going for a deposition. So what happens is, so during the straining, since there is a deposition is happening, so there is an internal stress is induced inside during the deposition. So one way of actuation is taken care because of the heating, and the other way of actuation is taken care because of the internal stresses which we are trying to induce it on the surface. Okay, so this this is a kind of arrangement. So what we are trying to get it. Okay, so this concept is called as Bimorph, where we have where two layers are there. So one layer is participating towards one way of actuation, and the other layer is participating towards the other end of actuation. Okay, so for our experiment, so what we did is, so we went for a Kapton polyamide, and we went for a copper-based shape memory alloy in the boat, and we made it in the form of a pellet. So with basically it's a kind of a ternary alloy. So this ternary alloy is made it in the form of a pellet, and then we have just fused this pellet in a vacuum environment, and then we have kept this pellet inside the boat, and then we have heated the pellet so that there is a continuous evaporation which is happening, and this evaporation will be depositing it on the Kapton polyamide, which is being strained using a kind of arrangement over here. Okay, so in fact, this is how your this is how our SMA Bimorph works. So this is a hot plate. So we are just trying to put it on a hot plate. The actuation happens because of the hot plate. When I try to lift it back, it comes back to its state. So when the student lifts it back, you can see it comes back to its state. So this coming back option is happening because of the internal stresses which is being induced, and the flattening is happening because of the shape memory effect which is available. Now, so this is a completely new concept which we have developed. How we are going to characterize it? So for characterization, so we have developed our own setup. So when we try to look into this characterization, so one, we all know I need to study the surface morphology. So surface morphology means basically which includes scanning electron microscope to see how the structural behaves. Then the structural behavior of it. So as far as structural is concerned, so I may need to do some kind of Xrd analysis. Shape memory alloy property is concerned. So there is a concept called DSC, which we call it as differential scanning calorimetry. So the main application of the main functionality of this DSC is, this DSC will give us a clarity about the austenite phase and the martensite phase of the material. So like it has a phase transformation behavior. So we can just study the phase transformation both in a hot condition as well as in a cold condition. So in a hot condition, what we do is we can just supply a temperature to it. And in the case of a cold condition, so what we do is, so we can go for a low temperature up to -180. So we have a capability to go from -180 to 650 degrees Celsius to study the transformation characteristics, okay, using DSC. And then in order to study the perfect actuation behavior, so the option which is available with us is a reliability test setup. Actually, we have developed a small reliability test setup, basically to understand the behavior of this shape memory alloy actuation. So in fact, this image is taken from in our laboratory, where we could see that initially this is the shape memory alloy Bimorph at room temperature. This is being clamped to a plate. So when you try to heat the plate, so there is a kind of actuation which has happened, which is something around at 150 degrees Celsius. You can see an opening up of this shape memory alloy, and at 250 degrees Celsius, there is a further elongation which has happened. Okay. Now, so these are some of the characterization we have done. So one with respect to surface morphology, where we could see a kind of a surface behavior on the surface. This is with respect to an Xrd analysis. So in an Xrd analysis, so we could get a clarity about the beta phase and the alpha phase of the shape memory alloy which is available. Because here in this case, what we are doing is we are trying to fabricate a shape memory alloy from the pellet to the final deposition. Okay, so obviously there will be some kind of secondary phases, but the influence of the secondary phases needs to be looked into it in an appropriate manner. Okay, and this is a kind of a Dsc analysis which we have done. So this Dsc analysis will give us a clarity about the austenite phase, austenite start, and the austenite finish of the shape memory alloy structure. So basically, if the DSC, generalized DSC of a shape memory alloy structure, so we'll have something like this. So it will have an austenite start, austenite finish, martensite start, and a martensite finish. So this will help us, this characterization will help us to narrow down. So what is the window at which you can use this material for a particular application? Like I have mentioned earlier, that for nickel titanium, we go for 80 to 130 degrees Celsius. And in the case of copper-based shape memory alloy, we go for 250 to 300 Celsius. So So that window is taken care using this Dsc analysis. Okay, and this is a kind of a TG analysis which we have done. So it's a kind of a thermogravimetric analysis which we have done to see how does the system behave. Okay, so now when I was just talking about this life cycle behavior of this shape memory alloy. So in order to study the life cycle behavior of the shape memory alloy, so we have developed a small setup, something like this. So in this small setup, there is a programmable power supply which is available, and there is a copper-based shape memory alloy, and there is a laser displacement sensor over here, and then there is a data acquisition system over here. So what we are trying to do is, so in this programmable power supply, so we are connecting this copper-based shape memory alloy over here, and then there is a laser displacement sensor which is available. And the main application of this laser displacement sensor is it has a source and it will have a detector. So what happens is from the source the light will fall and then it will get reflected back to the detector. So we have a copper-based SMA biomorph. So when this copper-based SMA biomorph, it has a reflecting surface. So when there is an actuation which happens, so this reflecting through this reflecting surface, the laser will move back and forth, and from this we can estimate what is the life cycle which is happening. So it is something like this. We can check the frequency of the shape memory alloy. We can check the response of the shape memory alloy, and we can check the overall behavior of the system. So in fact, this is the life cycle behavior of the shape memory alloy. That is, on the heating cycle, how does it behave, and on a cooling cycle, how does it behave? Okay, so what we are trying to do is, so this is a kind of a single cycle where a heating has been performed to see how much is the maximum displacement we could see. Okay, so slowly when you try to increase your heat, so with respect to displacement, we could reach up to 1.5 centimeter displacement. And when you try to cut off the heat, it comes back, there is a good amount of quenching which happens, and this quenching will result in returning back to its original state. So this is one option where we are trying to apply more amount of current to achieve a maximum displacement. So this is one option. Another option would be like on a small intermittent level. So I need to have a higher order frequency. That is, like for example, if my displacement is something around 2 mm, so within this 2 mm, I would like to achieve a higher order frequency. So when there is a higher order frequency is there, so I could see the overall behavior coming out of it. So basically I can just predict my shape recovery out of it. Okay, so this is one important aspect with respect to characterization of this shape memory alloy. In fact, this the main motto of doing this experiment is, so we want to vary the substrate thickness, because we have two materials which is taking part. So one is a polyamide and the other one is SMA. So when two materials are taking part in my functional aspects, so there is a chance that, so when I try to increase my polyamide thickness, so I can go for a slightly higher order frequency. So basically, if I want to go for a higher order frequency, appropriately I can just vary my thickness, or if I want to go for a lower order frequency, then I can go for a less thickness. Okay. So we want to investigate what is the influence of different thickness. So for that, we chose two different types of polyamide. One is a 75 micrometer polyamide and another one is a 50 micrometer polyamide. And we could see that how the responses behaves with respect to a 75 micrometer polyamide and as well as with respect to a 50 micrometer polyamide. So basically at 50 micrometer polyamide, we could get a proper narrow down system. Okay, so this is at 50 micrometer polyamide, and with respect to a variation in voltage, so we could achieve that there is an increase in the displacement which is happening. Okay, so at 50 micrometer polyamide, let us consider if my voltage applied is 3 volt, so I could reach, we could get a displacement of something around 4.5 mm. Whereas with 75 micrometer polyamide, so with the same near to around 3 volt, we could achieve a displacement of something around 9 mm displacement. Okay, so with this we could get a higher order frequency, and most important thing is we want to study the overall what is the life cycle behavior of it. See whether am I getting the same results throughout, even if I go for more than 1 lakh cycles also. Okay, because here you may ask me a question. So it is a deposition on a polymer. So there is a chance that more we try to actuate, the film may peel off from the surface. Okay, but the interesting part in this is, since we are doing the deposition completely in a vacuum environment, in a controlled atmosphere, inside a thermal evaporation unit, so we could observe that even after 1 lakh cycle also, the removal of the material was not happening. So which was completely interesting, and which is completely encouraging. Okay, so this is a kind of characteristics which we have studied with respect to displacement and with respect to number of cycles, and we have varied the voltage, and we have used 2 different samples, one with 50 micrometer and another one with 75 micrometer. So with 50 micrometer we could see the overall life cycle behavior, and at 75 micrometer we could see beyond 500 cycles also there is not much variation is observed. So basically we could go up to 1 lakh cycles. So we have used this Bimorph for some kind of robotic applications, and we have also proposed this for some kind of transformer oil sensing. I think I have a picture on this transformer oil sensing. So what we have done is, so we have kept it inside a transformer, and we have seen its behavior. Okay, so I'll be showing you that picture. So the interesting part in this is, like for example, you might have heard about this transformer failure. So in most of the transformer failure, so there is a coil which is available, and this coil will heat the transformer oil. So there is a repetition in cycle of this heating and cooling of this transformer oil. Okay, so there is a need to reduce the. So what happens is, there is transformer gets failed or transformer gets blasted only when there is a contamination is happening. So this contamination and the oil will change the property of it. Obviously, it will hamper the overall growth of the system. So the interesting part in this is, so we have used this material to immerse inside the transformer oil. So as and when the property gets changed, so appropriately you can see a variation happening on the surface. So for that, we want to do some kind of structure growth. That is, we want to change the overall behavior of it. That is, we want to investigate the influence of its substrate temperature, that is growth temperature, towards the different development of biomorph. So we went for 100-degree deposition, 150-degree deposition, and 200 degrees of deposition. Almost the phase transformation were almost same, but when we try to look into the recovery part of it, so this the samples with 150 degrees Celsius showed a better displacement as compared to the others. So that's how we have narrowed down the thing, and this is how we have studied the life cycle behavior of it. So basically, we would like to go for a higher order frequency. That is so we want to study the influence of frequency, or I would like to say that we want to manipulate our frequency for the required actuation. Okay, so basically, so that you can use it for some kind of dragonfly arrangement or some kind of micro robotic arrangement. So this is a graph which we have achieved, which we have measured using our setup. So to get a closer view, so we made a small Arduino board kind of arrangement to go for a different frequency and to see its behavior. So here you could see, so this is with respect to different frequency. This is with 1 Hertz, this is with 2 Hertz, and this is with 5 Hertz. So at different cycle, so this is at 5 Hertz. So this is at 1 Hertz, this is at 2 Hertz, and this is at 5 Hertz. So the control strategies are implemented using a small Arduino board microcontroller, and then we were trying to actuate it and see its performance. Okay, so this is how we have used this shape memory alloy biomorph inside a transformer oil. So this is a small transformer oil setup which we have developed. So inside this transformer oil, there is a bus bar kind of arrangement which is there. So and then we have kept a transformer oil in it, and we have immersed the shape memory alloy inside it. And there is a small laser displacement sensor coupled with an IoT system we have integrated. So what happens is, as and when the biomorph gets actuated, from the LDS sensor will be helpful for us to capture the signal, and then when the displacement exceeds, so from that we can tap the signal, and then it will be fed into the IoT system. As an extension of this, so we have also fabricated a small shape memory alloy engine. So in this shape memory alloy engine, what we have done is, so this is a kind of a perpetual motion, which we call it as Johnson's heat engine. So in this, so there is a pulley kind of arrangement which is there, and in this pulley kind of arrangement, so we have a shape memory alloy bell. So there is a hot and a cold junction which is available. So because of the variation in a temperature gradient, there is a continuous rotation which is happening, and then we are using a small dynamometer, and using this dynamometer, we are trying to harvest the energy. Okay, so this is a kind of waste recovery arrangement which is there. So in this waste recovery arrangement, so like any kind of hot water, if you take, you can just harvest the energy. So, but only thing is, appropriately we may need to arrange this. So this we have performed in collaboration with one of the industry. So what we thought is, we will make a belt kind of arrangement, an SMA Bimorph belt kind of thing, so that this belt will be fitted in between the pulleys. And then when you try to apply a kind of temperature transformation, so there will be a rotation of the belt, and from this we can harvest the energy. So this is a complete experimental setup which we have developed in our laboratory. So what we have done is, we have developed a small flash operation unit. So this is a kind of pulley arrangement which is available. So inside this pulley arrangement, we have a SMA Bimorph belt which is available. And this is a hopper, and then there is a boat which is available. So when this hopper vibrates, the material will fall into this boat, and then there is a continuous heating of the material which takes place, which leads to transfer of the material along the surface, and then it moves. Okay, so this belt deposition can be done even using sputtering, which we have a capability towards it. So this is how we have incorporated inside near to a vehicle to study the energy efficient characteristics. Okay, so before going into the next case study, so is there any doubts or questions?
Sir, yes, sir, I have a small doubt.
Yeah, please.
So what are the benefits of shape memory polymers compared to shape memory alloys?
What is, sorry, actually, hello, what is the difference between the, hello?
Sir, what are the benefits of shape memory polymers compared to shape memory alloys?
Acha, shape memory polymers compared to shape memory alloys. Okay, see, as far as this shape memory alloy polymer is concerned, it is highly restricted with respect to temperature, because these Nephron-based polymers are used for such kind of shape memory alloy polymers. They cannot withstand temperature beyond 100 degrees Celsius. So anything below 100 degrees Celsius, if you would like to work, you can use shape memory alloy polymers. Whereas shape memory alloy is concerned, so it has a flexibility, it gives you a flexibility to work anything beyond 100 degrees Celsius. Like for example, see here we have a shape memory alloy belt kind of arrangement. So this belt is completely deposited with a metallic material. Okay, so that is the reason I can directly use it in front of an exhaust. Okay, so the removal of the material will happen at a later stage, and it can withstand the overall temperature, and still you can harvest the energy. Okay, so that is the main advantage of going for a shape memory alloy material than a shape memory alloy polymer. But shape memory alloy polymers are used in some kind of microfluidic applications.
Okay, sir. Sir, how are shape memory polymers are made, sir?
Okay, most of the time, shape memory polymers are made through chemical routing. Okay, so that is with my understanding. In some cases, they also go for some kind of organic coating or spin coating, etc. They go for shape memory alloy polymer.
Okay, sir. So which one is better shape memory based material, like a polymer or alloy or ceramic?
Okay, see, like for example, it basically depends upon your application. As far as the response time perspective point of view, shape memory alloy and shape memory alloy polymer both are in the same plane. Okay, so but when we try to talk about the application perspective point of view, so I always go for shape memory alloy, because I feel working with metal will be more comfortable than working with polymer. So it basically depends upon your application.
Okay, thank you, sir.
Any other questions? Okay, so if there are no questions, let us go to the next case study. So if you recall the challenges involved in it, so one of the important challenge is like getting a customized shape. Okay, so currently in the recent scenario, we all know getting a customer shape of any material, obviously one important concept which comes into our mind is additive manufacturing. So because additive manufacturing or 3D printing will give you a capability towards it gives you a capability in manufacturing component, so based on your requirement. So with this as an idea, so we also had some work in mind. So we were trying to develop some kind of shape memory alloy structures for some kind of industry 4.0 applications. So in that, what we did is, so like so we want to make a small SMA ring kind of arrangement. So this ring we would like to put it up inside a collet, and then we were trying to apply a heat to it. So in this collet, so what we do is, so we for example, this is a spindle which is available. So in this spindle arrangement, so I am just trying to put my tool in this. So how do we know that tool is going to fail? So as and when a tool, like for example, let me just take a simple drilling machine. So if a tool is going to fail, means basically the tool will when the tool is becoming blunt, it will induce a chatter or a kind of a vibration, and then from that heat will be generated, and finally it will end up in failure. Okay, now since heat is getting generated, so since our material is responsive to heat, so what we thought is we will make a small shape memory like tool holder or a collet kind of arrangement. So this collet kind of arrangement will be surrounded along the spindle, and then whenever there is a vibration is there and whenever there is a heat is there, this shape memory alloy will get actuated and it will try to arrest the vibration. So when it tries to arrest the vibration, it damps the what you call the drill bit characteristics, and from that you can pull it up. Okay, so for this, so we took a route of additive manufacturing. So basically, this was done in collaboration with RRCAT. So basically, it's a very good DAE center. They deal with high energy lasers, etc. So we have a good friend, Dr. C.P. Paul. So he has an equipment, so which through which it's an indigenously developed laser additive manufacturing system. So where there is a coaxial feeder which is available. So through this coaxial feeder, we can just feed the powder. So since in our case, it is a kind of a nickel and a titanium. So we just use nickel powder over here, and we have induced a titanium powder here. And here there is a fused area which is available. So the laser is being focused in that fused area where it gets heated up. And when you try to manipulate it, so you can get the structure. So their system, it is a 5-axis system. So in this 5-axis system, there is a coaxial feeder, and through this coaxial feeder, the powders are being placed into it. And then there is a 2 kilowatt fiber laser which is available. So this 2 kilowatt fiber laser is made to focus on the material. And then there is since there is a 5-axis workstation is there, we can manipulate to get any kind of structure. So since we require such kind of structure, so we took a small plate. So over the plate, we try to deposit the shape memory. So this is completely a new concept, so which we are trying to fabricate through additive. This work was done in 2015. So in fact, our paper was the first paper to come up with the additive of shape memory alloys. So we need to do a complete analysis of it, and we need to do a complete characterization of it. Since we are using this material for some kind of industry 4.0 application, as well as some kind of machine tool holders, etc. So one important thing which needs to be done is like I need to study the mechanical. I need to study the influence of different process parameters. So this influence of different process parameters includes the wettability of the material when during the deposition, and then wettability and the catchment efficiency of the material of the process during the deposition, and then the surface morphological analysis, which is nothing but the SEM micrograph. And then we were more interested towards the structural properties of it. So here there is a need to study the mechanical behavior of it. So we need to study the mechanical characteristics of it. And then we also need to study the Dsc analysis of it. So what we did is, so we went for a different composition. So one composition is something like since we have a capability to go for different compositions, because we have 2 feeders. So through these feeders, appropriately with respect to weight percentage, you can change the powder, and then you can feed the powder. So so that it will also support our challenges which we have addressed in the first slide. So what we are trying to do is, so we went for different composition. One is 50%, another one is 45-55, and another one is 55-40. So by changing it, we went for a different microstructure analysis. We went for a complete mechanical properties analysis. So as far as mechanical property is concerned, so we went for a micro hardness testing as well as a tensile testing to see its behavior. And most important, we went for a Xrd analysis. So in this Xrd analysis will give us a clarity with respect to the amount of beta phase which is available. Okay, so this beta phase basically ensures how much is your shape memory effect which is available on the system. So with that, we were trying to look into the beta phase characteristics of it. So we went for a NATA different combinations, and with respect to my peak, so we were trying to identify the grain size behavior of the system. Okay, and this is kind of a Dsc analysis. So where we took a conventionally available shape memory alloy samples and the samples which we have fabricated with laser-based additive methods. So the conventionally available system. So this is characteristics of the conventionally available system, where we could see a sharp beta phase peak, which is a beta phase peak which is available, and there is no secondary phases which are available over here. And this is a kind of a Dsc analysis. So in the case of a Dsc analysis, so we can see an austenite start, austenite finish, and a martensite start and a martensite finish. So this is the one which we have fabricated using the setup. So where along with the beta phase, we could also observe some of the other phases which are available. And in addition to this, so almost similar, only there is a mild shift is there, but still almost we could get a prominent identification of the austenite phase and the martensite phase. Okay. So as an extension of this, so since we have fabricated this structure, we could observe that mechanically there were some kind of issues we could observe on the samples, because here in this case, the material is completely heated up, and then we are trying to manipulate the structure. So when we are trying to heat it up, so obviously there is a chance of certain amount of properties in the system. So in order to improve its properties or enhance its properties, so basically we may need to go for some kind of post-processing. So one post-processing, what we went is for some kind of annealing, and another set of post-processing is towards laser peening. So the main important aspects of laser short peening is to rectify the porosity, and the laser annealing is to improve the capacity, improve the crystallinity. So basically, the idea is to go for a uniform crystallization with respect to the laser. So in the case of laser peening, what we had is, so we had a sample. So over the sample, we have just pasted a black tape, and then we have inserted the sample in an underwater condition. And using a laser, we were trying to irradiate it on the surface, and then we were trying to heat the material, and then we were trying to impart a shock wave on it. So in the shock wave, what we had is, so we had a kind of water layer. So over the water layer, the laser was made to focus on it, and then using a shock wave, we were trying to induce a compressive residual stress. So this compressive residual stress can be helpful for us to reduce the porosity. In the case of laser annealing, so what we did is, so we used a laser to scan through the entire sample, so back and forth, and the scanning was done in such a way that, so there is a continuous overlapping which happens. So there is a 50 and there is a 90% overlapping we went, so that we try to crystallize the entire area using laser annealing. So this is a kind of block kind of structure. So here in this case, we have gone to the next level. So because in the earlier directly using nickel titanium, we could observe that it was just hampering my ductility. So whereas with respect to copper, so you get an improvement in the ductility with NITAC. Okay, so we could fabricate a brick kind of structure. So in this brick kind of structure, we were trying to study the characteristics. So we went for a this is with we could easily see a difference, where this is with the nickel titanium 50%, which is supposed to which was superior in the earlier studies, and with NITACU, so you get a refined grain structure which is capable enough in such a way that it can have a very good mechanical properties. Okay, so this is a kind of a DMA analysis we did. So in this DMA analysis, so we can measure the storage modulus of the system, because here when we try to look into the functional aspect of it, so we are trying to impart there is going to be a certain amount of impact which acts on the surface, and with respect to temperature condition, so this impact needs to be studied in detail. So basically, so we go for so this is with nickel titanium 50/50, where we could easily identify our austenite phase and a martensite phase, whereas the loop was not closing. Whereas in the case of NITI-CU and NITI-CU10, so we could see a proper loop which is coming out of it. So basically, this helps us to narrow down what is our martensite phase and what is our austenite phase, and how these systems can be used for a direct functional applications. So the interesting part in this is, so till date, it is very difficult to manufacture a customized structure. So here we could manufacture a customized structure and we can use it for an, we could attempt it for an application. But only challenge which was involved in this particular case study is the material was getting melted and reheated. So since the material was getting melted and reheated, so the property of the material was not to a level as compared to the commercially available system, which was evident from the Xrd analysis, where we had a beta phase. Okay, but it doesn't matter. For us, we were more concerned about the actuation. So, but we could observe that with this particular technique, so there was a drawback in the actuation. So whatever actuation which we were expecting, so we couldn't get it. So for that, we tried for a different technique. So like we almost took a similar application where we were trying to make some kind of SMA spline. So in this SMA spline, consider this as an arrangement. So where there is an SMA spline which is available, and there is a jaw which is there. So when we try to actuate this SMA spline, this jaw moves back and forth, and you can hold it. Okay, so similar to earlier structure, so we need to fabricate a small circular ring, and when we try to dice it, we get two spline. So one spline we can keep it over here, and one spline we can keep it over here, and then we can use it for this. Okay. So for this, in order to fabricate such kind of structures, so we developed a small experimental setup in our laboratory. In fact, we developed a small additive manufacturing setup in our laboratory, which we called as wire arc based additive. So in this wire arc based additive, so what did we do is, so we took a small gas metal arc based welding unit. So we have manipulated the gun. So we developed our own code. So using an Arduino board, we have developed our own software, so that whatever CAD files you are giving, so that will be getting transformed into a form of a proper CNC, and from that it will be fed into the XYZ stage, so that you can fabricate the structure. So in fact, this machine is completely developed at IIT, and we have also sold this machine to some of the private colleges for educational purpose. So this is the overall capability of the machine. So with this machine, we could fabricate a sphere of 30 centimeter by 30 centimeter dia sphere could be fabricated using this. Okay, and this is how we have bisected our system in the form of a spline. In fact, the interesting part of this machine is, so this machine we have developed in our institute dedicatedly for shape memory alloy. So by considering that, so we have made the bed in such a way that the substrate heat, the bed has a capability of substrate heating as well as the substrate. So in the case of substrate heating, what we do, we just apply an electrical biasing so that we can heat up to 650 degrees Celsius. In the case of substrate cooling, so we have made a small copper fin kind of arrangement, so through which we can just pump a liquid nitrogen into it, and then we can quench it, so that you can go for a tailor-made crystallization, and you can take care of the thermal property of it in an appropriate way. Okay. So now we have fabricated the structure. Now we are more interested to know the overall actuation behavior of it. So in fact, this is the as fabricated NITA. So we have diced it in the form of a thin sheet, and then what we have done is we have gone for a SMA twinned martensite. Then we have gone for a martensitic plate. Then when we try to put it in hot plate, it comes back to its shape. I think I have a small picture of it. Yeah, see, so this is a small graph sheet which is kept on top of a hot plate, and this is the SMA which is being fabricated with our wire arc additive. So since we have fabricated in the form of a circular form, so we have just diced it and we have kept it on it. So when we try to actuate it, it gets displaced. Okay, so we did a Dsc analysis as well as a Xrd analysis. So with respect to Xrd analysis, we were trying to investigate the austenite phase and the martensite phase. And then with respect to Dsc analysis, we could somehow narrow down our austenite start, austenite finish, and the martensite start and the martensite finish phases. Okay, so we also had a certain amount of R phase, a rhombohedral phase, which was observed in the system, and this is a kind of a mechanical testing which we have done on it. Now let us go to the next challenge, which we called as thermomechanical analysis. So before going into it, so in a nutshell, we have discussed about an additive manufacturing of shape memory alloys. In the case of additive manufacturing of shape memory alloys, we have discussed about two different route of additive manufacturing of shape memory alloys. One is with respect to laser base, another one is with respect to wire arc base. So in both the cases, we have investigated in detail, and with respect to wire arc base additive manufacturing, we could achieve a proper actuation coming out of it. So any questions or any doubts in this?
Sir, I have one small doubt, sir.
Yes, sir.
Compared to wire arc based additive and laser based additive manufacturing, if I'm going to choose for shape memory alloy like a filament type in a FFF manufacturing process.
That is, you mean to say friction? What do you mean by FFF?
Fused filament fabrications.
Okay, so filament means then see here it is a metal. So you want to use a metal wire?
Yes, sir. The shape memory alloy, it's like a filament type of metal wires.
Okay, so you would like to use a filament type of metal wire for a fused deposit. Yes. Yeah, please carry on with your question.
Sir, which one is better? Because the filament fabrication FFF is low cost process compared to wire arc and laser additive manufacturing.
Yeah, I agree with you. But the thing is, in the case of filament process, will your nozzle will be capable enough to supply a heat of something around 650 degrees Celsius? Because you need to melt the shape memory alloy.
Okay, sir.
Okay, see, in the case of laser, we have a high energy falling on it. So that is the reason when I just pour my nickel powder and the titanium powder, exactly at the focal point, my energy is going to be huge because I'm using a 2 kilowatt laser. So my melting temperature will reach something around 750 and 850 degrees Celsius so easily, so that the material melts and then we are manipulating it, getting this. In the case of wire arc also, what I am doing is I am creating an arc. So like in your welding so basically it's a welding setup. So inside this welding setup, I'm trying to feed the nickel titanium wire into it. So because of the arc, the wire melts and then we are trying to. But I am not sure, but if your fused deposition has a capability to go up to 650 to 750 degrees Celsius, then with nickel titanium it is possible. But I am not sure. Will it be possible?
Okay, sir.
That is the main constraint which I have seen when I was considering this particular system. Okay, because compared to laser, I felt that wire arc was much cheaper to me because welding gun costed me something around 75 to 1 lakh. And then other manipulation stage and everything, I could integrate it by getting it, I could retrofit it by getting in bits and pieces, so that the overall cost of the entire machine came only to 3 to 4 lakh. Okay, so with 3 to 4 lakh, I have a capability to manufacture 30 centimeter with 30 centimeter square, which is quite good. But the problems, I also understand that you will be having certain amount of change in mechanical property, but somehow we are trying to rectify it by changing the substrate heating, etc. All those things. Okay. So that is what the story. Okay. But obviously there are other methods are also there. So people are also coming up with other methods. Even people have attempted with the E-beam also.
Sorry, sir. One of a research paper I literatured by using a shape memory alloy in FFF additive manufacturing. So that's why I'm asking.
Might be, sir. Might be because they might have used nozzle which can have a high temperature. So that option is there. Should not be a problem. Okay. So fused deposition means what I understand is you are trying to spread the spread the material on the surface, and then you are trying to use a medium to heat it. Am I right? Or you are using a nozzle?
Yes, sir. Yes, sir. Yes, sir. You have to fabricate it triple from them into cold furnace or furnace itself. Then it get some mechanical, improve the mechanical properties.
Acha. So in that case, then it's a kind of where we are using a furnace to reach its particular temperature, and then you are doing it. Okay, so then it is possible.
Yes.
It is possible. It is possible. No.
Thank you, sir.
Any other questions? So if not so, let us go to the next case study where we are trying to study the thermomechanical and the life cycle analysis. So as far as this thermomechanical and the life cycle analysis is concerned, so this is one of the key characterization for such kind of shape memory alloy structures. For example, I am I'm a company person who is dealing with shape memory alloy spring, and I want to use it for some kind of air conditioning system. So when I try to use it for air conditioning system, so there is a chances there that as a customer, you may ask me a question that what is the reliability and what is the warranty of the shape memory alloy structure, which is completely, I may need to look into it before supplying it to the customer. So for that, so commercially, there are no standard procedures which are available to investigate the behavior of the shape memory alloy structure. So this is one setup which we made it in our lab. In fact, we have patented this also. So this setup is a reliability and a life cycle test bench. So in this test bench, what we had is, so we interfaced, we made a fixture kind of arrangement. So in this fixture, there is a SMA spring which is connected to it, and there is a pulley, and there is a load which is being connected to the pulley. So this SMA spring, when I try to actuate, there is a mirror which is available, and then I'm trying to actuate this SMA spring using a programmable power supply. And then there is a PC and a DAC, and then there is a thermocouple which is fitted to it. So the main function of this thermocouple is to estimate the temperature which is happening. Okay, so I am using a small PID controller, and then there is a kind of a interferometer kind of arrangement which is available. So this back and forth movement of the SMA spring is monitored using this interferometer. So this interferometer will try to pick up the signal, and then we can study the overall life cycle behavior of it. In fact, this is how the life cycle of the SMA structure comes. So this is an SMA. This is a kind of a heating cycle and the cooling cycle for the SMA response, and where we could see a displacement. In fact, since it's a spring, we could go up to 20 mm displacement. Even the forward stroke is happening because of the load which I am applying to it, and the reverse stroke is happening because of the power which is being involved given by the power supply. Okay, so this power supply will try to close my SMA spring so that it will try to pull back to its state. So this is a kind of small reliability setup which we have made. So this is with respect to electrical actuation. Now, so since heat is by major key, so what we thought is, why can't we explore some options where we can go for remote based actuation? That is, you keep the shape memory alloy somewhere at a particular distance, and using a laser, if I try to supply a incident on the surface, so we can see its actuation behavior. Okay, so with this as an idea, so we had a small fiber laser with us. So with this fiber laser, we were trying to study the behavior. So what we did is, so we had a continuous laser and we have a pulse laser, and then we also had this is a kind of a contactless energy transfer. So using this contactless energy transfer, we were trying to heat it, and we were trying to study the characters. So in this contactless energy transfer, again we also used a hot water connection. So in this hot water, so you keep a fluid. So inside this fluid, you're trying to heat the surface, and you can study the behavior. So the idea behind this is, first, using a laser. So we would like to see the overall performance. How does it behave? So like because it has its own advantage of seeing its it has its own advantage in actuating the shape memory alloy in a remote location. Okay, so this is the overall experimental setup which we have made. So in this experimental setup, we have a fiber laser, we have a spring, and then there is a load, LDS, a DAC, and a computer. So this laser will try to scan through the spring. So when it tries to scan through a spring, So the load will get first the load will pull. So because of it, there is an elongation which is happening on the spring, and when the laser is incidenting on the spring, it tries to scan through the spring and it comes back. Okay, so we used we almost varied our power from 5 watt to 50 watt and see its overall behavior of it. So at low energy, how does it behave? How does it behave? And at high energy, how does it behave, etc. Okay, and with respect to number of turns, with respect to wire diameter, and with respect to coil diameter, how does it behave? So this is a kind of temperature profile which we have done. So this is an SMA spring. So you can see the laser is just passing through the temperature profile and the actuation happens. Okay, so one option is you have a outer diameter coil. So on this outer diameter coil, how does the laser pass through it and how does the actuation behaviors? And we were more interested to know how does the conduction happens over the entire region. So this is a kind of a conduction behavior. So where the laser is made to irradiate through the coil and see its actuation performance. So this is a kind of a fiber laser which we have used. So in this fiber laser, it's an yttrium doped fiber laser, and this is a kind of a shape memory strip which we have come up with, and you could see. So we have just tied a weight to it, 100 gram and 150 gram. And the laser is made to irradiate on the strip. And we could see the actuation behavior. Okay, so now we were more interested to study the overall life cycle characteristics of it. So for that, what we made is we made a small LDS sensor. And using this LDS sensor, we were trying to study the life cycle behavior. So we have a displacement and a time. So with respect to displacement and time, and by applying a different load, so we are just changing the power. So one is with 50 watt, another one is 20 watt, 45 watt, and the one with 50 watt. So with 15 watt power, we could achieve a displacement of with 1.5 Newton load. There is a displacement of up to 10 mm was achieved. Okay, slowly when we try to increase the power, the displacement was also getting increased. So the maximum displacement we could achieve is something around 30. So if we would try to closely observe the overall life cycle behavior of it, so there is a kind of a continuous heating and cooling which is happening. So when this continuous heating and cooling happens, there is a continuous variation we could see, and we could tap the signal coming out. So these are some of the various laser actuation characteristics which are available. So we were looking into the importance of different process parameters. So one process parameter is with respect to number of passes. So by changing the number of passes, how does it behave? And then we were also trying to look into the heating and the cooling characteristics of it. So this is with respect to the heating characteristics, and this is with respect to cooling characteristics. By varying the power along the conditions, we can see the variation. And these are some kind of studies with respect to applying load and the variation in the displacement and along the power characteristics. Okay, the most important is with respect to laser power and with respect to actuation time. So because we were more concerned about the actuation speed. So how does the actuation speed imparts on the surface and how it has its own applications towards the functional behavior of it. So we did some kind of a theoretical simulation to study how the laser-based interaction works and how the laser-based interaction is being incorporated on the surface to get the required actuation. So as an extension of this, so in the case of a non-contact mode, so we have a laser-based actuation as well as we have a kind of a hot water-based actuation which is there. So in the case of laser-based actuation, so we have developed a small experimental setup and with a laser displacement sensor, and we have to study it. The case of hot water based actuation, so what we did is we had a small pulley kind of arrangement. So over this pulley kind of arrangement, so we have kept the shape memory alive, and then we are just trying to put a hot water into it and see its performance. In addition to this, so the earlier one what we have shown is a continuous laser. So we were also more interested to know the influence of a pulse laser. So in the case of pulse laser, what we did is we used a small cylindrical lens. So using a cylindrical lens, we converted a spot into a line. And this spot into a line is made to impart on the this one on the shape memory alloy spring structure, so that we could see the heat which is being incident on the surface will try to create some kind of coalescence on the layer, and when it creates a coalescence, it will induce certain amount of stresses on the surface, and then it will somehow improve the actuation behavior of it. Okay, so this is a kind of response which you have achieved with respect to hot water actuation, and this is with hot water actuation where we could see the heating and the cooling cycle. This is with respect to cooling cycle, and this is at heating cycle. And in the case of laser-based actuation, you get a proper heating. So with respect to pulse laser, so the interesting part is so with respect to pulse laser, we can go for a higher order life cycle. Whereas with the case of a continuous laser, it has its own limitations. So that is one major advantage of going for a pulse laser-based actuation system. Now, so this is just to give you an overview how a non-contact based actuation can be employed, and how do we investigate the life cycle behavior of this non-contact actuation. So for that we have done. Okay, so the next challenge which is on our go is welding of this shape memory alloys, because welding of this shape memory alloy is a challenging task. So people have attempted using different welding, but our main motto is after welding, in most of the cases, this shape memory, it loses its shape memory alloy property. Okay, so for that, one option what we went for is, so we took a friction stir welding, because we all know friction stir welding is a less heat dissipating process, so that it will not impact the property of the shape memory alloy. So the interesting application of welding of this shape memory alloy is, so when you try to weld a shape memory alloy structure, you can, and if it gets actuated, you can use it as an intelligent aerofoil structure. So when it is used as an intelligent aerofoil, so you can have the loading on your aeronautical engine will come down, and then you can have an improved efficiency. So this is what is an idea. Okay, so and so for that, so this is a kind of an arrangement what we have. So this is on an initial portion where we do an welding. When we try to actuate it, there is going to be a deflection which happens on the surface. So these are some of the characteristics. So where, since it's a heat sensitive, we may need to select the welding appropriately. So wide varieties of people have attempted. So using gas welding, using resistance welding, using electron beam welding, plasma arc welding, laser welding, etc. So here we are talking about a friction stir welding. So in the case of a friction stir welding, so we used as so it has a forging pressure. So that is a frictional heating plus a forging pressure is applied to it to get a higher strength bond, and a lower temperature associated with the friction stir welding will lead to a lower residual stress as well as a less distorted compared to the friction stir. Okay, so this is a friction stir welding machine which we have used. So this is a specially designed fixture for holding thin sheet. So an NITA SMA structure is kept over here. So we are trying to hold it, and then using a tool holder. So we are trying to move along the line of the joint to weld it in a proper way, and this is the thickness of the joint. So this is a closer view of the friction stir welding. So in fact, this is a kind of a tool design which we have done for it, and this is how our weld zone was looking like. In fact, you could see that there is no any kind of damage or any kind of interface layer is observed with respect to nickel titanium. And then we had an arrangement in such a way that, so there is a pin arrangement, and then there is a transverse which is available, and using this transverse we could just instant on the surface. So we did some kind of sample preparation. So we went for a certain amount of furnace annealing on it, and with respect to furnace annealing, so we were trying to see the capability of it. So we had two materials. So we have just used a kind of a friction pin over it, and we have welded it, and we have studied the phase transformation coming out of it. Okay, so this is overall picture of a friction stir welded shape memory alloy structure. So this is initially in the temperature phase, and when we try to apply a temperature of something around 65 degrees Celsius, there is an elongation which is happening. So this is exactly the weld point where, if you see, so there is no breakage which is happening on the surface. I think I have a small video about it. So this is a kind of a hot plate studies. So this is at 65 degrees Celsius where you could see a very less response, and at 75 degrees Celsius we could get a higher order response. So in fact, at 65 degrees Celsius, the time taken to recover the strain is something around 22 seconds, and at 75 degrees Celsius, it is around 13 seconds. Okay, and here there is a weld joint which is available, which is not hampering your actuation. So this is an interesting part with respect to NITI shape memory alloy. So in order to study the recovery angle, so what we did is we made a certain kind of arrangement, something like this. So in this arrangement, so we have just applied a load to it, and then we are trying to apply a heat to it to get the actuation behavior. So using a Dac, we were trying to harvest the energy. So this is a kind of a theory of actuation which we have employed. So one is with respect to displacement and with respect to time. So we were trying to study the heating and the cooling characteristics. Basically, we were trying to study the martensite to austenite and the austenite to martensite behavior. And then we were also interested to study the electrical actuation at different amperage conditions. Okay, so the idea what we got from this is like we could estimate, or we could directly fabricate the shape memory alloy structures using friction stir welding process. And the most important thing is, since we could directly get and weld a defect-free structure, so we could directly study the actuation characteristics in a much better way. Okay. So the next, any questions on this? Any questions on this welding? Okay, so if not so, let us go to the next thing. See, one of the major aspect with respect to SMA is integrating a composite structure. Okay, so like one important aspect with SMA is basically we have a variation in temperature condition. So when there is a variation in temperature condition is there, obviously it will have its own impact towards the actuation behavior. So now if we are using it for some kind of aerofoil behavior, so one option which is available is if we can integrate a shape memory alloy inside a composite structure, so that whatever temperature we can just whatever weather condition is there, that won't have an impact on it. Second thing is we can make an intelligent structure out of it. So as far as this SMA integrated composite structure is concerned, so we are trying to develop a small aerodynamic behavior, an aerodynamic structure. So in this aerodynamic structure, so there is it has its own potential application either into the form of a windmill arrangement or in the form of some kind of low actuation systems. So in the case of windmill arrangement, so we have a composite layer. So inside this composite layer, suppose if I am integrating such kind of shape memory alloy structure, and if I am trying to actuate it, so you could see a deflection, and this deflection can be somehow helpful for us to create a drag force, and then you can have an increase in the speed. Okay, like based on your air, you can just induce a certain amount of actuation to the SMA wire, and then it will result in a drag force to it, and you can have a continuous rotation to harvest more energy. This is one application. Another one application is towards an aerofoil structure where you have an aerodynamic, and then when we try to actuate it, this aerodynamic structure will move. Okay. Another important aspect is something kind of a lightweight, low power, and it has a high efficiency system. In fact, it has its own potential applications in some of the automobile industries where SMA integrated automobile car bodies can be employed, so that it can result in a lightweight, and most important thing, as and when there is an impact is there, by supplying a heat to it, you can just unbuckle it, and then it can come back to its original shape. This is one advantage of going for this kind of composite structure. So with this as an idea, in fact, we want to test the capability of shape memory alloy in integrating with both GFRP as well as CFRP. Okay, so we went for a composite fabrication. So first, in the case of composite, before going into this composite fabrication, so we want to do certain amount of SMA training. So in order to do the training, so what we did is, so we had a small training setup. So towards this training setup, so we were trying to integrate the shape memory alloy wire in it, and we were trying to apply a kind of loading to it. So when you try to apply a loading, so it will result in a kind of strain on the surface. So when there is a strain is there, so basically the maximum strain we can go is up to 12%. So beyond 12%, the SMA will lose its shape memory alloy property. Whereas when you try to manipulate your strain from between 2% to 8%, appropriately you can get a different deflection coming out of it. So with this as an idea, so we had a small fixture. So in this fixture, so we have kept a constraint and we have tied our shape memory alloy within those fixtures, and then we have tried to apply a kind of constraint to it, or we have tried to give a strain to it, and over which we have tried to fabricate the composite structure. Okay, so this is a kind of system where we have used a concept of SMA training, where we have a kind of fixture. So inside this fixture, we are trying to keep this shape memory alloy wire, and then we are trying to change the shape to it. And this training is we are doing a training in such a way that first we are just integrating it inside a furnace, and then we are quenching it in a cold condition. In most of the cases, we were going in for some kind of brine solution, or in some cases, we were also going for a liquid nitrogen, so that when we try to quench it, it tries to come back to its, it tries to regain, remembers its shape. So basically, we are trying to memorize the structure on it. Then we went for a continuous composite deposition. So this is a kind of a smart composite structure. So this is a kind of a characterization which we have done for some kind of SMA based composites. So what we have done is we have used a power supply. So this power supply will be integrated inside this SMA composite structure, and there is an LDS layer which is available. So, and then there is a Dac system. So this Dac system will try to capture the data from the LDS. In the meantime, this programmable power supply will be highly helpful for me to give a variation with respect to different life cycle. Okay, so with respect to the heating and the cooling cycle, so I can study the behavior of the system. Okay, so this is how we have fabricated our shape memory alloy structures. So we have just used a SMA wire, and then we have integrated a composite structure into it, and then we are applying a straining to it, and then we are trying to fabricate a SMA structure into it. So we have used a fiber and a resin, and in this fiber and the resin, so based on your orientation, you can just integrate a SMA structure appropriately. So for us, we are using for aerodynamic structure. So we were more interested to create some kind of twisting and some kind of twirling on the structure and see how does it behaves. Okay, so for that, so we went for a different configuration. In fact, one configuration is something like this. So you have a composite, and we have just kept 2 wires into it. And by actuating these 2 wires, we could see how does the system behaves. And this is with respect to integrating the shape memory alloy inside a glass composite and see its functional behavior. And this is something kind of a configuration where we are integrating more amount of wires inside the layer. Inside the layer. So that what happens is this deflection takes place. Okay, so when we try to deflect it, so we can see the so variation in the structure which is happening. So this is a kind of a 2 layer. So with respect to the heating and the cooling characteristics, so we could see the to the life cycle behavior. Okay, so and this is on a single layer where we could directly study the heating and the cooling behavior. So this is how the structure looks like. In fact, this is how we have fabricated our shape memory alloy structure. This is the side view and the front view of it, and by integrating SMA wire into it, we could study the deflection. So this is with cooling, and this is with heating. Okay, so here you could see a video where you could see how it is getting deflected. So this is the frequency at which it is getting deflected. So I can get any kind of orientation. So appropriately, only thing is I may need to program my wire, and then if I need to get a deflection in a forward stroke, then appropriately I may need to program my wire in such a way that the deflection will be in the forward stroke. And if I need to get it in the reverse stroke, so I may need to program my wire in a reverse direction so that it gets deflected in the opposite direction. So it is something like this. Like I just program it in such a way that here I get a 2% strain, Here I get a 4%. Here I give a 4% strain, and here I give a 6% strain. So by giving different strain, we could achieve a different actuation characteristics. So in fact, this is one configuration where we could we want to have a complete deflection, or I would say a complete twisting. So in the case of a complete twisting, so what we had is, so one layer we have kept the shape memory alloy below, and on the other layer we have kept on top of it, and then we have made a sandwich layer out of it. And then by giving an actuation, so the one layer gets actuated, it tries to deflect in one direction, and the other layer gets actuated and it tries to get deflected in the other direction, so that this twisting can appropriately help in different orientation of the system. So these are some of the complete dynamic analysis which we have done. So we were more concerned about the frequency, and we were more concerned about the deflection. So already we have seen how does the system works. So we could see we have taken this end reflection angle by using a laser displacement sensor, and we have just using the programmable supply as a power supply, we are switching between the heating and the cooling cycle and see its behavior. So this is a kind of a switching which is happening with respect to heating and the cooling cycle, and the change in deflection which happens along the surface. And this deflection will be highly helpful to study the behavior of the system. So either we go for a 4-wire system, we go for a 8-wire system, or in some cases we can go for a 6-wire system. Most important thing, since we want to integrate this system in some kind of aerodynamic structure, so obviously the environment will be different. So one option what we did is, so we want to try the performance of it, basically the actuation behavior in a low temperature condition. So in the case of a low temperature condition, and so what we do is we made a arrangement through which we were trying to pass a liquid nitrogen into it, and then when we try to actuate it and see on the liquid nitrogen condition how does it behave. So almost in the hot condition as well as in the liquid nitrogen condition, it was drawing an appropriate power, and due to the frequency and the response is almost matching with the requirement. Okay, so this is what is the heating cycle what we achieve, and this is what is the cooling cycle. Now the last session is how we have used this shape memory alloy for some kind of soft robotic application. So currently we are focusing in this particular direction. So basically this shape memory alloy has a capability towards biomimicking capability. And so that is one important aspect with respect to shape memory alloys. So we have used this shape memory alloy to fabricate some kind of fish kind of structure. So one kind of fish kind of structure is, since we have an expertise in using a wire, so we have just integrated this wire so we have just programmed this wire, we have strained this wire appropriately, and we have made a 3D printing structure to mimic such kind of fish kind of structure. So almost we took a complete body of a fish, similar to a fish, and we went for aerodynamic modeling. And with respect to aerodynamic modeling, so we have fabricated the structure of the fish, and then we have fabricated a kind of 3D printed the structures, and then we have, instead of bone, instead of that nerve, we have replaced that nerve with shape memory alloy, and then we have developed our own controller. It's a simple on and off coupled with some kind of Atmo based system, so that based on the movement it can biomimic. And then there is a skin kind of arrangement. So we have wrapped the structure with the skin. Okay, and then now this is a kind of a controller board which you have worked. So this is how we have fabricated our shape memory alloy based fish. Okay. So this basically a complete SMA spring is used, and the buoyancy is taken care by the 3D printed structure. As an extension of this, since we have just integrated with the composite, we have also manufactured some kind of jellyfish kind of structure. So this is one work which we are currently continuing. Okay. So this is a work which we have developed in our lab. So this is a original jellyfish, and this is the jellyfish which is being manufactured using a shape memory alloy. So we could actuate it, and almost this is a kind of a orientation along a vertical direction, and this is orientation along the horizontal direction. So we are trying to biomimic these systems. So with this, I would like to close my lecture for today. So I would be happy to address any kind of questions or queries. I think tomorrow I also have a session on amorphous silicon. So we have worked on laser-based processing of amorphous silicon for photovoltaic application. So I'll explain. So any questions or any doubts, queries?
Thank you, sir. Thank you for a wonderful session on manufacturing and characterization of shape memory alloys. Dear participants, any doubts you want to clarify with the expert, you can ask.
So basically, it's a wide spectrum of work related to shape memory alloy, which we have performed in our laboratory. So by identifying some of the key areas, we have addressed it. Okay, so if there are any questions, you can just write to me. So my email ID is palani@iitta.ac.in. So in case you want to use any kind of facility, you are free to use it.
Yes.
Okay. So
thank you, sir. Thank you for very informative. Thank you, sir. Thank you, participants. So we will start the 4th day of the FDP on tomorrow. From the first session, it will start at 9:30 a.m. as per the schedule. Thank you all.